Well, this is a special lecture because it is the last lesson. And why is it the last lesson? Well, two reasons. First of all, it's lesson number 40. And that's a heck of a lot of lessons. I mean, they also are a lot longer than I expected them to be. And they're about an hour each. That's 40 hours. That's a lot of hours. But I think they were good. I like the level of detail that we went through, and we got through all the topics. And the section on forms actually took up a lot of the last part. So if you really cut out that, I still think we have a very comprehensive course about the mathematical nature of tensors, or at least the elementary story. And it's more than enough to get us started on what we really want to talk about, which is general relativity. So 40 hours, that's one of the reasons it's over, but also we're done, right? We've got the whole idea of how tensors operate. We kind of understand this picture, right? Where we have space-time, let's see, I guess x1, x0 with x2 and x3, and at each point in space-time, we have all of we have the tensor product, we have the tangent space, or the space of the vector space V, the V dual, all of the tensor product spaces that you can have, right? V dual, right? And then all of the exterior power spaces, right? V dual, wedge, V dual, etc., etc. And they're located at every point in space. We understand how the connection, right? The connection allows us to compare vectors at two different spaces. We understand the covariant derivative, the Lie derivative, all of those operations acting on tensors, producing new tensors, and the exterior derivative, right? So there's three types of derivatives we learned. We learned about the three types of derivatives, right? So that's the Lie derivative, the covariant derivative, and also the exterior derivative, right? We learned about all of those, and those are the only ones. We've got this idea, the weak spot here is we've got this idea of space-time with all of these things put together on top of the space-time. But we really don't have the notion of a manifold, right? I didn't go into that in these lectures. However, I did create a whole separate section lessons on manifolds, and I really do think that the first bunch of those is a really good idea to read up on, because this stuff here is a little bit hand-wavy, right? Oh, we just have lay down a coordinate system and plot some points and create your vector space at each point and build a connection to bind them together. I mean, that'll work. I think that'll work. That'll get you through elementary GR. But if you're serious about the subject, you've got to study manifolds. And of course, to study manifolds and understand them, you kind of have to have a grip on topology. And I cover all of that in the What is a Manifold lectures. However, when we do general relativity, when I do the next set of courses, the next set of lessons on what is general relativity, I will probably make it a prerequisite at some point in the course that what is a tensor and what is a manifold combined together will form the prerequisite for the other class. But not all 40 hours of this course will be required. I think up through the derivatives. We got the three derivatives. In fact, up through the first two derivatives, we can even wait on the exterior power. So I'll make the prerequisites up through these two derivatives and probably some fraction of the manifold stuff. Maybe not all the way through fiber bundles, maybe up to fiber bundles. That's probably what it will be. It'll be up to but not including fiber bundles in this lecture series, and then up to and including, or I guess I should say through Lie and covariant derivatives. And between that stuff, you should have no trouble with elementary GR, and we'll get those lessons started. Then when we get more and more advanced, we'll start adding the other topics, and they'll become prerequisites as well. But for this last lesson, I want to talk about one final thing, which is the coordinate basis. Since we were talking about visualization, the coordinate basis of arrows stacks, sheafs, and honeycombs. And what else did we have? Arrows, stacks, sheaves, honeycombs, and thumbtacks, right? Each of these are a vector space, right? Each of these represent one of these elements in this structure that we've already kind of built many times. This is all for three-dimensional space because our visualization stuff has been going on in three-dimensional space. And each of these can be visualized. We've been working on that, and hold on. Lambda 1. Right, so we have our sheafs. These are our sheafs. These are our honeycombs. I'm sorry, sheafs here, right? Thumbtacks. Okay, wait a minute. Arrows here, right? Thumbtacks here. Stacks here. Honeycombs there, and sheafs are here. And sheafs, as we know, are isomorphic to the honeycomb. Okay, so, but each of these has a coordinate basis that can be visualized too, right? We already know how to visualize the arrows coordinate basis, right? The coordinate basis of arrows are three little arrows that we usually depict as to be orthogonal. So what does orthogonality necessarily mean now? Well, in the coordinate basis, we're assuming that we have coordinates on a manifold. So once we assume we have coordinates on a manifold, we can understand coordinate planes, right? Coordinate planes. And that's planes of where one of the coordinate values are kept constant. And in three-dimensional space, they will literally be planes. So, for example, in regular standard Euclidean coordinates, you might get a coordinate plane, and you imagine that these are infinite planes, of course, where we have some value of x1. And then we might have another coordinate plane that would have another value of x1, like that. And then, of course, there could be a coordinate plane with some value of x2 and some other value of x2, and that would be the I'm building it up as a cube, right? So this surface and this surface of the cube would be x2's constant coordinate plane, whereas the front face and this back face would be x1's constant coordinate plane. We write x2. And then, of course, with obviously the top and the bottom would make up x3. And you end up having this little cube in Euclidean Cartesian coordinate space. What's important to understand is that for any coordinate system, right, if it's a useful coordinate system, you're always going to end up with little cubes, no matter what the coordinate system is, spherical, cylindrical, or anything, as long as you consider these differences between the front surface and the back surface of the plane you're interested in to be small enough. So if you had, for example, a cylindrical coordinate system, if it was slightly, let's say, macroscopic, it would appear, the cube would appear like this. You'd have a square on the sides. The front and the back would be, let's see, how would I have to do this? That's a bad drawing. Hold on. Let me try one more time. You would have, let's see, well, from the top, it would look like this, right? And then the cube would go into the plane. So let's see if I can make it look like that. Something like that. And then there would be, and so it's getting to be a cube, but it has to be very small. It has to be very small so that this arc and this arc are virtually flat and have virtually the same curvature. So this has to be small to keep it the same curvature. This has to be small to keep it flat, but ultimately when it does so, it ends up limiting to a cube. Same thing with the sphere, right? A sphere will kind of look like, oh, now it's gonna be really bad for me. A sphere will end up kind of looking like, that part will be straight. But this will be curved and that'll be curved, right? But again, once you make it small enough, it ends up being a cube. So the point is, no matter what coordinate system you've got, whether you have spherical, cylindrical, or rectilinear, or any of the others, you squeeze everything small enough, you end up with tiny itty bitty cubes that fill up space, chopped up by the coordinate planes, right? So from this tiny little itty bitty cube, we're going to imagine and understand the unit vectors of each of our different kinds of objects that we've been working on visualizing. Now the problem is of course, is that this little cube is inside the coordinate space, right? We're talking about x1, x2, and x3. This is our space-time, right? Now, again, we're only doing 3 dimensions, so it can't really be space-time. But we're now thinking of the space, or usually the right word would be the manifold. So the manifold has these coordinates on it, and manifolds have coordinates on it by definition. That's what manifolds really are. They are things that can be made to be given coordinates. So when we talk about objects that exist on or in or around this cube, we're thinking of things that extend in space. But that's a problem because we know that if we're going to define unit vectors, each of these vector spaces exists in its own little place, right? In space, out sort of separated from space, floating out there, but attached to each point. But we're going to define the unit vectors of each of these different vector spaces in terms of a tiny piece of space. So clearly we're going to be thinking of this in terms of a limit, right? The limit where all these things are cubes, so that's the first thing. But the objects we define using this cube don't actually live in this space. They live in a separate space, and we have to understand that. For example, if these, I'm going to draw arrows, right? And if I draw an arrow here, like that, well, you might think it would cover several cubes. But if I drew an arrow here, what if it goes so far that it actually starts to having to curve with the coordinate system, right? You don't want to worry about those kinds of crazy things because they're not important. What's important is that this arrow doesn't live in the space. It lives in some separate other space, and in that space it defines a unit vector, right? Because we're going to show how it defines a unit vector. Well, let's start with the example. Let's start with the arrows. So if this is our point in space P, then we have right away, after we build this cube, we have arrows that go in each direction, in the direction of these cubes, of the edges, right? There's 3 edges, so there's going to be 3 arrows. Let me get this last one in green. Damn it. And so that will define the directions of our units, of our unit vectors. Then we just establish the length that we want, and that sets the scale, and those will be the unit vectors. Now, again, they don't live there. They're going to live in a 3-dimensional vector space that is sort of attached to this whole thing. And this 3-dimensional vector space here is attached to this point, but the vectors in it are associated with these 3 directions, right? So, and once we define this little cube, we get these 3 dimensions, these 3 directions. Now, ultimately, we can even understand this in terms of, as we take this limit and get things smaller and smaller and smaller, then we can understand how these things can be thought of as partial derivatives in each of the different directions. How would I write that? Sorry. D mu, like that. And this happens basically because we are considering a limiting process where this is getting smaller and smaller. And that limiting process is going to ultimately be the core of what makes this a derivative. Not worth worrying about too much. What's important to understand is that the coordinate system itself will define the basis vectors at every point. But that one you know about. But also notice that it defines a stack at every point too, right? It defines, for example, there's this back plane of the cube, and then there's this front plane of the cube. And those are 2 parallel planes that have a definite distance apart that would establish a density of a basis stack. In this direction, it would be say the x2 stack. I guess you have to give it a direction. because the stacks always have a direction. But that would be a basis stack. And likewise, the top of the cube and the bottom of the cube would also define a basis stack. And then the sides of the cube too. So you get 3 basis stacks. What's nice about 3 dimensions is everything has 3 basis vectors. So you get your 3 basis stacks. And then this logic just continues for everything. What else can we pull off of this cube? Well, you could pull off a bunch of arrows, not one arrow, but a bunch of arrows going through each corner of the cube. Now, if all you care about is the direction and the density of the arrows, if that's the only thing that matters, direction and the density of the arrows, now you've got your sheaf. Remember, the original arrows, you cared about the direction and the magnitude of the arrow. The magnitude of the arrow. Here we care about the sheaf, we care about the direction and the density of the arrows. So that makes up the basis sheaf at that point. The thumbtacks are really easy because the front plane of the cube, or the back plane of the cube, because it's got to really touch the point. Some part of this thing has got to touch the point. I'm going to make it really dark because I've got a lot of scribbles going on. That thing there, that is your basis thumbtack. Likewise, you can have a basis thumbtack down here. Now remember, the stack, both planes mattered because you need the density of these infinite planes, right? The planes are infinite in size for the stack. It's their density that matters. But for the thumbtack, it's the other way around. It's the planes are a finite area, and there's only one of them. The one that we would want is down here. You want it so it touches the point that you're asking about. So I drew it up here, but that's kind of a mess. The one down here, that would be your basis thumbtack, and it also is given a direction. And then, of course, there's a basis thumbtack right here also, right? So there's a basis thumbtack too. So the thumbtack basis is pretty clear. The honeycomb basis isn't tough either. The honeycomb basis is just what's crammed in between the sheaf, right? The sheaf kind of makes its own little honeycomb, so that's your honeycomb basis. And the densities are important because that's the scalar. So the ones that don't have 3 dimensions are the scalar ones, right? So the scalar density, well, first of all, regular scalars don't even have a basis, right? So you don't have to worry about regular scalars. But scalar densities, let's see if I can get a new color here. How about this green? Scalar densities would involve taking these points at the vertices of the cube, and that creates a density, that creates a density. So you've got this little swarm of points. I think Weinreich likes to actually call it a swarm. A swarm of points, that is your basis for your scalar density. And the volume of the cube itself is your basis for your scalar capacity. And that covers everything, right? It covers stacks, it covers honeycombs, it covers arrows, thumbtacks, sheaves, right? And it covers your scalar density and your scalar capacity. Ouch, this green is really horrible. Wait a minute, I want my red back. So that's how you sort of understand these basis vectors. As long as you're careful to realize these are basis vectors for the vector space that's actually attached to the relevant point, right? That's what this was supposed to mean. All right, so that kind of concludes our efforts to do the visualization of forms. And it also concludes our lecture on what is a tensor. I think we really have covered a lot of ground, and if you've come this far and you've followed this far, I really do hope that you dig into some of the books that are out there. In particular, at this point, you really should be able to pick just about any general relativity textbook and start reading. I'd stay away from some of the more crazy advanced ones. I'd stay away from Wald until you finished a more elementary one. But I definitely would feel free to do Dinvernio has a great textbook. Hartle has a good one. I mean, there are a lot of good ones out there, and a lot of them are free on the web too. And those things will cover this material again. and it's probably going to be even better. They will all use the. They will almost all use the. Where's my? They will almost all use the component notation, right? I've already talked about that a bunch. They will their tensors and vectors will always look like a mu nu alpha beta like this, or without any unit vectors, right? But now you know. Now you know that those unit vectors are floating around out there, and that's what they are. They are, and that's why your indices are ordered the way they are. Now we fully understand that. And when we do what is what is general relativity, ironically, I'm probably going to drop into that too. It's so much more convenient. Once you understand why it's there, you can use it all day long. The problem is there's a tendency to introduce it and never quite grabbing what it all means and why it is the way it is. But now we know. And if you're not comfortable yet, that means you probably move too fast through this course. And that can happen. I get very enthusiastic when I'm learning new things, and I move too quickly. And I inevitably end up going back and filling the gaps. And I don't know if that's a good way of doing it or a bad way of doing it, but we will use the component notation a lot in what is general relativity when the time comes. Okay, so thank you very much, and I'll see you in the next set of lectures.